Alright, today, it's Coach Stricker, and I'm here to talk to you guys about the electrons in the quantum model, okay? And so first things first, we're going to review a little bit about where we were at in the quantum model. We were at the Bohr model. Remember, the Bohr model was the one that said it had the nucleus with the protons and the neutrons in it. In that nucleus, there was protons and neutrons, and then outside the nucleus, we had those energy levels that had electrons in them. And Bohr said that electrons are in the outer shells like planets orbiting the sun. So it's called the planetary model. Well, a lot of scientists kept researching and researching and researching and realized that that wasn't correct, that there was actually energy levels, but that electrons don't actually go around in circles. They actually just, they're always bouncing, okay? And they're popping, pop, 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 pop. And then what we're going to see when we're done with this is that the quantum model is going to be made, and that the electrons are actually in probability distributions. And a probability distribution is regions of space where the electrons most probably are. Okay? Now, those electrons are in atomic orbitals, all right? And that's the areas of space where the electron that contains the electrons. So those probability distributions, we're going to find out later, are broken up into atomic orbitals. That's a whole other day. But that's what we're going to finish with, is the quantum model. Now, back in the day, Max Planck was the first scientist that quantized energy. He looked at light and said light is a particle, and he developed the quantum, which is a packet of energy. So he looked at the light as a particle, all right, and developed the idea of the quantum, which is like a packet of energy that light gives off. All right. Then Albert Einstein looked at light as a particle, and he calculated the speed of that particle. So he used his speed of light formula, all right, and came up with E equals mc squared, and then they adapted that to the energy equals Planck's constant times the frequency, which we're going to go over in a little bit. All right. So Einstein developed the speed of that particle. Max Planck saw light as particles. And then Bohr and Rutherford came along, and remember, Bohr was the guy that came with the Bohr model. Well, he kept studying it. Well, they discovered the quantum model for hydrogen, okay? And they looked at just the simple atom of hydrogen that has, one proton and one electron. And what they saw was that one electron, when they heated it up, would jump to a different energy level. And then that was unstable, so then it would fall back down. Now, that energy level where that electron is called the ground state. That's the lowest energy level that it can be at. That's the ground state. But then it would gain energy and it would jump up to a different energy level. Well, that's called its excited state. So the excited state is the energy, is when electrons gain energy and jump to a higher energy level, but it's unstable. And so what do they end up doing? They end up falling back down to their ground states. Okay? And so when they fall back down, they saw that light was emitted. Okay? And that light energy was called a quanta. All right? So that light energy that was emitted was called a quanta. And so they realized that this isn't just happening for the electrons of hydrogen. This is happening for the electrons of all of these elements and atoms. So Schrodinger came along, okay, and he was from a different camp. Schrodinger said, you know what, I don't think light is particles. I think light is in waves. And he studied the electromagnetic spectrum and had all these experiments that showed light acting as waves. And he was correct. And so he saw, that the wavelength was the length of a wave from crust to crust or trough to trough. Excuse me. The wavelength is the length of one wave. All right? Now, the frequency is how many waves you have per second. And the reason why those matter is because we're going to use those in our equations in a little bit. But Schrodinger worked with light as a wave, and he came up with this wave theory that really helped scientists understand what was going on with these electrons and the energy. And then de Broglie came together, and de Broglie was kind of like, hey man, can't we just all get along? You got your particle scientists, you got your wave scientists. He's like, look, light can be both. And so he talked about the duality of light. And what does dual mean? It means two. So it's the two natures of light. And it can be a particle, light can be a particle and a wave. So that was de Broglie. Well, de Broglie, you know, he had his math formula too that we're going to look at in a little bit. But and his whole thing is that you know, there's experiments that show that light can be a particle, and there's experiments that can show that light can be a wave. But there is not an experiment that shows light as a particle and a wave at the same time. And that led to Heisenberg's uncertainty principle, which said that it's impossible to know both the speed and location of an electron. That you can find the speed and you can find the location, but you can't know both the speed and location of an electron. And so that's what led to these probability distributions. What they would do is they'd take snapshots of where these electrons are. And they would see, okay, that first electron is mainly in that area. And then they would do another one and they'd say, okay, well, let's follow this electron. Well, that electron was mainly in this area. And then this electron was mainly in this area. And so basically it was like that first electron is mainly in this space right here. All right, and then that next electron was usually in this space all the way out here. All right, and that led to the discovery of the different atomic orbitals. All right, and the different atomic orbitals are where we see the electrons today. All right, and so now what we're going to talk about is those light equations and how we're going to use them in math. So we're going to slide on over here. All right, and the first thing we're going to review again is when we were looking at the ground state, remember that was the lowest energy state of an electron. So it's down here, gains energy. So to be able to go from the ground state to the excited state, you have to gain energy to do that. Then that energy is going to come off in light that we can see when it falls back from the excited state to the ground state. It gives off quanta. And what's a practical example of that? Fireworks. When you guys go and see the 4th of July fireworks, those are elements, okay, and they're heating up those elements' electrons, and then they get to a higher energy level or higher energy state, the excitement state, and then they fall back down and they release, you know, frequencies of light, which you can see different colors. And so that's a great example of being able to see that. And different elements give off different colors. It's kind of like it's, you know, costume or it's MO. It gives off different stuff. All right. So when the electron falls from the excited state to the ground state, it releases energy called quanta. So that's important to understand that. And we're going to be seeing that when we do flame testing. All right. Now the light is given off, and we can calculate that frequency of light and its wavelength. So when we see that light that's given off, we can actually calculate its frequency, its wavelength, and its energy. How do we do that? Well, we're going to use this formula here. And that is C equals wavelength times frequency. When we say, what? That's C. That's not. C is the speed of light, and it is a constant. It is always the same. It is 3.00 times 10 to the 8th meters per second, and it's a constant. So C is always constant. This lambda sign, which looks like an upside down Y, that is the wavelength. And the wavelength is measured in meters. And then this V is the frequency. And the frequency's unit is 1 over a second. So the formula is speed of light equals wavelength times frequency. Well, because the constant is the, you know, what it says it equals, we're never actually going to solve for C. So what we're going to do is we're going to be given 2 of the 3 things every time. They'll give you the wavelength and you can solve for the frequency, or they'll give you the frequency and you can solve for the wavelength. So these are the 2 formulas that go with that. If I'm given wavelength, okay, I take the speed of light divided by the wavelength, and I get the frequency. If I'm given frequency, I take the speed of light divided by the frequency to get the wavelength. So I can solve for frequency up here and wavelength right here. Now, if it asks me for energy, then I'm going to use the formula capital E equals HV. And capital E stands for energy, and that unit is going to be joules. The H stands for Planck's constant. So once again, we have another constant that I will give you, and you'll always have it. So you're not solving for H. H is a constant. It is 6.626 times 10 to the minus 34 joules per second. And you take H times V, which is frequency again, which is 1 over a second. So there's one variable that's linked to both of these formulas. What is that? What's the one thing that's in both formulas? Frequency. So because of that, if I'm given wavelength, I can solve for energy. You say, well, whoa, how do you do that? There's no wavelength down here. If I'm given wavelength, I can solve for frequency. And once I know frequency, then I can solve for energy. Just like if I'm given energy, I can solve for wavelength. How would I do that? Well, you would first solve for frequency using the energy formula, and then I would plug frequency in here and solve for wavelength. All right, so it's a two-step problem. So if they give me wavelength and ask me for energy, 2 steps. First solve for frequency, then plug it in. If they give me energy and ask me for wavelength, first solve for frequency, then plug it in, and you can solve for wavelength. All right? So those are the 2 formulas that we're going to be using in our math problems in this unit. All right.